All right. Well, hello everyone. I'm Justin Essery, Associate Professor of Politics and International Affairs here at Wake Forest. Well, actually, not here at Wake Forest University. I'm at my house right now. This is the International Methods Colloquium. We've been doing online meetings since before it was cool, but now due to coronavirus, I'm getting a lot of emails about how to do this. So probably seeing a lot more of this kind of interaction in the future. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. The IMC is affiliated with the Society for Political Methodology, who hopes that you will support quantitative research in political science by joining. The membership fee is just $10 a year for graduate students. I will post a link to join the society in the Zoom webinar chat window right after this introduction. This week's speaker is Jeff Gill from American University. His talk is entitled An Introduction to Dirichlet Process Priors for Random Effects and an Extension to Model-Based Clustering. Jeff's talk will last 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window, and you can ask a question anytime, but we will hold all questions except possibly for very brief clarifying questions until the end of the presentation. A link to Jeff's slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post that link to the chat window right after this introduction. Now I would like to welcome Jeff Gill to the IMC. Jeff, welcome.
Thank you, Justin. It's great to be here. Obviously, this is the safest way to give a talk right now, so no worries there. I wanted to talk today about, first about just Dirichlet process prior models in Bayesian regression, and then to introduce an extension that I'm currently working on, that I was working on maybe 5-6 years ago and then went into the file drawer, and now it's back out of the file drawer. So comments are definitely appreciated. So back to my slides here. So what are we doing initially? So we all know this usual random effects model here, right? So, you know, a linear model, Y is a model by X beta with this psi here, or as Andy Gilman calls it, the pitchfork. And then the psi sub j's distributed normal around 0 with a variance tau squared. And all the usual dimensions apply, as you see on the slides. And pretty much everybody knows this model and it's tremendously useful, and so on and so forth. The Dirichlet process random effects model that I'll be doing today replaces psi. That is, the distribution of psi is not going to be stipulated so specifically. It's going to be drawn from a Dirichlet process with 2 parameters, which I'll discuss in detail. So what we're doing is we're putting the Dirichlet process prior on the random effect only, okay? We're not putting them on regression coefficients because that is known to lead to bias. So what we notice from this historically is we have fewer parametric assumptions, we have more accurate estimates of the coefficients of interest, and therefore shorter credible intervals. This is actually called Bayesian non-parametrics, which is kind of a weird term because, as you see, there's a lot of parametric stuff floating around in here. But the fact that it's got fewer parametric assumptions, as you will see, leads to that name. So to do the measure theory, which we need to do here, Y, the outcome that I care about, is a random variable taking on values in some measurable space, curly Y, curly B, where curly B is an abstract space for the moment. The parameter of interest, and this is the big leap here in this literature, is P, that is the associated but unknown probability measure taking on values in curly P, which is the collection of all probability measures on curly Y, curly B. So we all are comfortable with the idea of random variables. That is, here's a variable, has a distribution. I want to estimate it as nicely as I can. Here, the unknown thing to be estimated, at least initially, is the parameter. I'm sorry, the distribution of the parameter. So the distribution is the unknown quantity. We have to give it some more details. Now we're going to define curly S as the smallest possible sigma field generated by sets as follows. That is, the P's such that P of A is less than R for all A subsets of curly B, and R lives between 0 and 1. the latter being pretty predictable. So that sets us up to define nu as a probability measure on curly p, curly s, which can be used as a prior distribution for the unknown p. So all of this is Bayesian. So if p is the unknown quantity to be estimated, I need a prior for it. I also want to obtain a posterior, which in my notation here is nu star, which is the posterior distribution of p given some data y. In this context, nu is a Dirichlet measure. If for every finite partition here of the parameter space curly b, that is the parameter space curly b of the unknown p, the distribution of p for b1 over b up to bk under nu is Dirichlet. And then the bottom two lines just gives the kernel of the Dirichlet distribution and then the requirements. That's pretty well known, but not necessarily in the notation in the context that I'm giving here. Okay, so that's the theoretical underpinning. And as I mentioned, the big leap is just the idea that we now have an unknown p to be estimated, not like the contextual standard unknown x to be estimated, or whatever to be estimated. So this literature is old in some ways. As you see here, the key papers are Ferguson's papers, his student Antoniak's paper. And what they did is they introduced this Dirichlet process that I'm going to describe for this non-parametric G, which you see down below. This is the probability measure on the space of all measures, okay? So that is, it's the mapping from some probability measure to all the possible expressions that it could have. The cool and interesting thing about those papers, at least historically, is they basically did almost all of the difficult measure theory, most of the difficult proofs. They're very dense annals of stats type papers, and they have no actual useful data analysis in them. And so if you look at the dates, that makes sense in the sense that they did not have the technology to actually estimate the models they were describing. And of course, we can do this now because we do. More on that in a minute. So the models they initiated, so G naught here is what's called a base distribution, as you see here. This is sort of like the expected value on the distributions. So we have random distributions instead of random variables. We still have an expected value or measure of centrality of some sort. The other important parameter is the concentration or precision parameter. It gets labeled different ways in different papers, and that gives the spread of the cylinder around G naught. So that's kind of analogous to a variance, obviously. When you put those things together, they're called a base measure. It's pretty standard to notate that as phi naught. And it gives us a specification, at least notationally, that G is distributed according to a Dirichlet process with lambda and G naught, which is a member of curly P. That is the collection of all probability measures that we're considering here. Okay, so any finite partition of the parameter space, that is K being a finite number, the joint distribution of these probabilities has a Dirichlet distribution according to what you see down below. And that's just notational, but it's a reminder that, that we are considering this as a Dirichlet. And then for an observed partition, what we get is a set of multinomial probabilities according to what you see there. So realizations of the Dirichlet, they select a discrete distribution with probability 1, right? Even though this mechanism is continuous. And so the model for the random effect vector is a countably infinite mixture. And we'll see specific expressions of that. So another important paper in the history of this literature is by Blackwell and McQueen. And what they showed is the following in a general sense. I'm going to do this for random effects only, but this is a general statement. So if G is a Dirichlet process, where we're drawing phi 1 through phi n, IID from that process, then the marginal distribution, right, that is marginalizing over any prior parameters, is equal in distribution to the first n steps of a Polya process. That's the second statement there. They also proved that the joint distribution of these psi's is the product of successive conditional distributions of the following form. So it's successive in the sense that drawing phi sub I is conditional on the phi 1s through phi I minus 1s that you've already drawn. And what you see here is this mixture distribution right? Where the lambda it plays slightly different roles in the two mixture components. And this is a Dirac delta function on the second part. So that is, the reference can be made to a finite rather than infinite dimensions given this setup. And this has been proven, as you see below. That's not the most intuitive message or expression of that. So it actually, when you define it within the Polya process, it does two things. It becomes a little bit more intuitive. That's the next slide. But it also sets up a recipe for Bayesian stochastic simulation. So let me move to that. Okay, so the Polya process, or sampling the size, is equivalent to the following steps. So imagine a restaurant with many large tables, okay? And what we want to do is we want to bin the diners. Actually, this is kind of ironic since I can't go to restaurants here in DC. We want to bin the diners at different tables, okay? And some diners are going to sit with each other and some diners are not. And those table assignments end up being the random effect assignment that they receive, okay? So obviously it's non-unique, it's gotta be less than n, and so on and so forth. So the diners walk in one at a time to be seated, and this is that successive notion from Blackwell and McQueen. Just to get things started, the first diner has to sit at the first table. So we have this lambda weight, this concentration parameter, which is key, and it helps us assign the next set of diners, okay? So the ith person comes in, they sit at the unoccupied ith table by themselves with probability lambda over I minus 1 plus lambda. Otherwise, they select an occupied table according to the other part of that mixture we saw with probability n sub j, and that's where the sum comes from. That is the number of people at that table over I minus 1 plus lambda. So what you see is the concentration parameter is key to how this binning or this table assignment is going to take place. Since if lambda becomes large, relatively speaking, especially relative to n, of course, then people are going to be more antisocial. They're going to sit at their own table with higher probability, since lambda is both the numerator and the denominator of the other part of the mixture. Okay, so now the table assignments are dependent exchangeable sequence as discussed on the previous slide. So we can also notate the set of non-empty tables, and this is a sample from the Dirichlet process, okay? So this is not what Ferguson and Antoniak and Blackwell and McQueen and a few others conceptualized. They were trying to estimate a single model at a single point in time using analytical procedures, but this sets us up perfectly for an iterative MCMC process. Okay. So here we are. That is, the y's are going to be distributed according to some parametric assignment, conditional on some set of parameters, which I'm just denoting theta here to hold whatever. And then, of course, the random effect components. That, of course, right, is just producting over the individual contributions, given the size, and the size come from that Dirichlet process. Well, it turns out Liu and Low, as you see the citations down below, they were able to derive an actual likelihood function from this procedure. And it's kind of an interesting likelihood function in a sense that it's pretty compact and you can see the components there, but it's not terribly useful in the actual estimation sense. So underneath the summation, what you see is the cardinality of C defines that summation. And this just ends up being a very awkward likelihood function to work with. And those two papers are super useful theoretically, but not super useful in writing applied modeling. Okay, so what we noticed over time, over a series of papers, is that not only does it make it intuitive, but it makes it a lot easier to sample if we reduce the parameter space. So one way to do that is to define this A matrix here. And the A matrix, what it does is it takes care, or it summarizes the table assignments from that restaurant algorithm. So the rows are defined, in my little contrived case here, a set of 6 people, and the columns define a set of 3 table assignments. So the first 2 people end up sitting at the first table, right? The cases 3, 4, and 6 sit at the second table, and then case 5 sits alone at the third table. And so what you can see this does is it maps from the size for I case, I equals 1 to cases, to a smaller set, which I'm labeling A to J. Uh, so exploring this a little bit more, there's the contrived example again. So instead of having the size in the expressions, we're going to have A times eta, right? Where A is what you saw, and then you see over on the far right-hand side, we've got a set of 3 etas or 3 table assignments or 3 random effects to go estimate on each iteration of the sampler. Okay, perhaps I'm going a little fast. So returning to that definitional statement, the theoretical papers give a recipe for defining a Dirichlet process for that curly P to be defined as all distributions in the world ever under any specification. It turns out it's a little more practical to limit it down a bit. In this case, I'm defining a Dirichlet process over all normals with mean 0. So my prior is going to be all normals that have the infinite number of normals that have mean 0. And then I'm going to preserve that tau squared variance parameter. Okay, so introducing the A matrix into that, it's the same statement basically, except as you see in the normal parenthetical part, it's x beta plus A times eta, and then sigma squared I, where in the standard way, where the eta is normal with mean zeros. Now, if we had the answer and we could do this analytically, it would lead to a very simple, compact statement of the normal linear model that you see here. That's interesting theoretically. That's not terribly easy practically. Hence the sampler. So a couple notes on this. So this basically summarizes in reasonably quick time the Dirichlet process prior literature, although it's vast now. So I'm definitely simplifying it considerably. Couple notes on that. It's not hard to find papers where people will take those table assignments, that is, they'll take those binning of cases to the tables, use some process, usually some post hoc thing, where they take those tables and they put some together and try and define substantive clusters, say in the social science sense that we're all familiar with. That is, if person I and person J sit at a table, say 80% of the time over 10,000 iterations of the sampler, maybe they're in the same substantive cluster. This actually turns out, as you see in my slide, is wrong for several important ways. First of all, those bundles, those table assignments, they are not substantive in any way. The process there is solely designed to use the random effect process to make the models fit better so that the beta coefficients have smaller credible intervals and the model fits better in general. Okay, they're not incorporating the covariates in a clustering way, in any way that's useful, and they're just temporary assignments in the context of the sampler to make the model fit better. Probably most damningly, there's no overfitting penalty in this Dirichlet process. That is, the model will split these people out to as many tables as practical, given the lambda parameter, in seeking to make it fit better. So if there's no overfitting penalty, we're not going to have a good connection to social science clusters. So as an example, at the end of the slides, there's some papers cited. In one paper, we were modeling 512 people that ran federal agencies in the United States, so senior executives at federal agencies. And so N was 512, and what we noticed was that in a typical iteration of the sampler, we would get about 200 unique table assignments. And we know there aren't 200 unique types of political executives. So that's not a proof, that's just an example. Okay, so what I want to do is I want to find an alternative, or at least an incorporation of an actual real clustering strategy. And so one possible alternative is the standard mixture model that you see here, right? So we're just weighting over mixture weights of each case to build the likelihood function. So we do the weighting over the cases with that summation. We product with after that to build the likelihood function. As you'll see, that's not a typically a productive way to do this. More usefully is the product partition model, which is given down below, where if we have a specified cluster configuration, then what we can do is we can build that clustering into the production of the likelihood function. So if I have this curly C, which defines binning of the cases in some way into M clusters, which has to be less than N, obviously, then that information can be put directly into the model. Since this is a Bayesian stochastic simulation approach, that C will change on iterations. So why would we do that? Well, some reasons not to use the mixture in this context is it lacks a model parameter, right? So we just have a set of weights. That's quite a limitation. It doesn't allow us to do cluster identification in the way I'd like to do. And then, of course, how do people do that? Well, a common strategy is to fix the M, the number of different mixtures, try it out, see how it looks. It doesn't look good. Okay, let's try another M. There's a lot of papers that do this with the boring hackneyed galaxy data, of course. And also in my context, the mixture model for Bayesian regression estimating with MCMC has an identifiability problem that you see there. I won't go into details for the sake of time, but it basically, and with standard setups, with standard priors, you have a non-identifiability issue. Okay, so why would I want use the product partition in this context for clustering? I'm not saying the mixture model is bad, just in the case that I'm interested in. It could be modeled efficiently. The search algorithm could set up to move across cluster space. We identify the cluster on each iteration, and we don't have a label switching problem. Okay, so what's up? In addition to the Dirichlet component for the random effects, I want to have this set of clusters where once we define a cluster in an iteration of the stochastic algorithm, I'm going to have a set of linear regression models uniquely defined within each cluster. And so what you see here is that same linear specification you saw before, but everything is indexed by curly L for being in the cluster L in curly C. So that means that we still have the Dirichlet process going on, but we have a unique set of identifying model parameters for each cluster curly L. These are non-nesting processes. That is, the Dirichlet process identifies the bundles to fit better. The clusters are what we have a substantive interest. So this is the worst graph I've ever made. I just can't think of a better graph. So the idea is to show the fact that these are orthogonal in the model. So the vertical yellow lines conceptually identify substantive clusters, and the green sort of horizontalish lines identify the Dirichlet process binning. And so people can be in the same cluster, but in a different bin, and they could be in the same bin in a different cluster. And by bins, I mean those bundles, actually. Okay, so it's a Bayesian model, and it's reasonably highly parameterized, so we need a whole bunch of priors. So the beta Ls, that is the regression parameters in cluster L, get a normal around beta naught, which is sort of a central expectation for those. Well, not sort of, it is, with a unique sigma squared L and a scaling parameter. Sigma squared L, as Bayesian conjugate tradition goes, gets an inverted gamma. As a reminder, the Dirichlet is that first line of the last block there. So phi naught, the Dirichlet process is around normal with tau mean 0 and tau squared. Tau squared is going to get an inverted gamma. The lambda gets a gamma prior. Then we get to the product partition. Beta naught gets another normal. Sigma squared beta gets another inverted gamma. That scaling parameter gets a Wishart, and actually an inverse Wishart. I'm only going to care about the diagonals. I don't have any reason to care about the off diagonals of that process right now. But how do you define a prior on cluster space? This is actually a weird and interesting challenge. Before we get to that, just a summary, right? Here is sort of in definitional terms what we're up to. So within each cluster, Y sub L is conditional on all the other data, all the other parameters, and the cluster configuration. And Y actually becomes analytically a multivariate T. We still have the job of estimating that with those exact parameters in that cluster. And then we also have a set of non-cluster parameters to worry about. But getting back to the prior on the number of clusters, what I didn't appreciate some time ago was just how complex and how big cluster space can be. So that's something I'd like to share today. So here's a really simple example because I have only 4 data points, only 4 cases. So if you have only 4 cases, okay, this is the set of partitions you can possibly have. So there are 4 cluster classes defined in the graph, R1 through R4. So you can have conceptually a cluster where everybody's in the same cluster. On the other end of the scale, you can have a cluster arrangement where all 4 cases are in their own cluster. And then you can have clusters defined by 2 and 3 categories, right? So you see that in those 2 inner boxes. So what we have is 4 cluster classes, 5 configuration classes, okay? And the notation for that is, as you see, is BNP. So that's the number of partitions of the integer n cases into p components, so p partitions. In the first case, the first box, B41 is 1, second box, B42 is 2, the next box, B43 is 1, and then finally B44 is 1 as well. So this is just 4 data cases, very simple, but obviously that's not very realistic, right? So again, as a reminder, right, we have the cluster classes, the configuration classes, and then we have the partition types, right? So the partition types, let me just go back. We have 1 partition type, 7 partition types, 6 partition types, and then 1 partition type here for these 4 cases. It turns out that the number of partition types, that 1761, is a Stirling number of the second kind, which you see there. It actually gets a lot worse than that. That is, there are, in this example, there were 15 possible partitions to worry about, which are clusters in the substantive sense that I care about. And that's actually a Bell number. As you see, Bell number for 4 here is only 15. But Bell numbers are known in mathematics to grow incredibly fast. So for instance, if I had 30 data cases, 30 people, 30 countries, whatever is being studied, the Bell number for 30, that is the total number of partitions, is 1 times 10 to the 24 roughly. That's interesting because that's roughly the number of stars in the known universe. So this is a huge space, and that's part of the challenge of this project. So I need a prior for clustering. So fortunately, there's 1 paper out there. So what this paper suggests is to put a prior on M, the number of cluster classes, draw from a Poisson, right, which is truncated between 1 and n. Actually, I want to make it 1 to n minus 1, but that's a minor detail. Making the intensity parameter something that you think is appropriate. The default in the paper is 1. I've played with that as a tuning parameter. It's not super important how you do that. And then that gives you N1 through NM partition types, which is great. So that's your prior on clustering. That gets you started. As you see down there, the number of unique partitions is that NP. We have to have that divisor there because if you don't divide out the number of non-unique cases, you have too many. So in the example I have down before, if Y3 and Y4 in the same cluster, it doesn't matter what order they got put in there. Okay, so the structure of the final model here is we have a bunch of cluster model specific parameters. That is, once we have a curly C, a cluster arrangement, then we have a bunch of betas and a bunch of sigma squares for each cluster. We also have upsilon here, which are all the other parameters to be estimated, which are the parameters from the ones that are not affected by clustering. So there's 2 things going on here. I need to hurry up a little bit. So the general process of the samplers, we're going to give sample the upsilon parameters, then we're going to generate a candidate cluster, then we're going to accept or reject that with a metropolis step, and then repeat, of course, many times. The challenge is, of course, mixing through cluster space. If there's a question on this, I'll come back to it. This is just me sampling the transition matrix in the process of doing the upsilon steps. We have to move through cluster space, this gigantic space. So how do you do that? There's a nice paper by Jane and Neil from some time ago where they do this split merge thing where they split up clusters and then they merge or split more clusters as a way of sort of randomly moving through cluster space. So we do that. Then we do a random walk, some small moves around the choice, and that seems to mix very nicely. So what do you do after doing all of this? So you end up with a set of clusters that you visited in the sampler. So one notion is, why not just say the probability of the clusters that you've observed is the probability, this is this big equation here, the number of times that you visited that cluster over the number of all cluster visits. So if I visit a cluster 15 times out of 100, right, it gets a posterior probability of 0.15. This is actually, I should have a curly equal sign there because this is only an estimate, because the size of cluster space is as such in realistic models that it is impossible to sample or to mix over the entire space. That turns out to be the challenge here. Ways around that I've been considering or implementing is starting at radically different parts of cluster space, being very analytical about looking around modal parts of cluster space. The problem is cluster space is impossible for humans to visualize in large dimensions. So that's a reoccurring challenge in this. I wanted to get to the application before Justin pulls the hook out. So this is a slide that basically says terrorism is bad and we should worry about it. This is another slide that says terrorism is bad and we should worry about it. This is a slide that says that terrorism data is bad and it provides a lot of challenges. So we're selecting in the outcome variable. The measurement isn't great. We usually don't have as many explanatory variables as we would like. We have non-ignorable missingness typically. We don't have access to things that governments have. Governments also filter these data, right, before we get them. We have actors that are deceptive, violent, want to hide. And we also know we have unmeasured clusters in terrorism data. So basically, terrorism data often violates every chapter of KKV. All right, so here's a nice data set. It's big, allied, and dangerous. So it's bad data in both senses, maybe. No, it's actually very useful data. This comes out of the group at the University of Maryland. So we have almost 400 attacks from 98 to 2005. In the data example I'm doing today, I took Al-Qaeda out since during this period, they're special. The outcome variable is fatalities. Let's see. So some interesting explanatory variables, whether the group is sponsored by a government, so part of the world, the size of the terrorism group, whether they hold territory, the alliances they may possess, and then there's left-no, relig, ethno. That's a variable name only a political scientist could make up. It's a 1 if the group's ideology is leftist and not compounded with another ideological orientation. Otherwise, that group's ideology is either not leftist or is a mix of leftist and other ideological dimensions. So you can stare at that for a while and it's still a little bit confusing. Whether they're pure religious, one group, purely ethno-nationalist, and whether they're dominated by Islam. So run that model, 10,000 iterations, 400 data cases. That takes about 5 days on a reasonably powerful 18-core machine. Assess the convergence in the typical way. Convergence looked fine using the typical tests and graphical tests. And this is actually the best I've done on any model, on any data with this setup. So 45% of the time, this cluster configuration that you see here, or something very, very similar. So I'm including one, if it was 271 and then 8 in the next, I'm counting that it is basically the same substantive cluster. So this is actually a really, really strong result. So what do I do with that? Several things. One simple thing to do is to just run two models and look at the differences. So what we have here on the left is just a regular standard Bayesian linear model with a single intercept, as you see up there, ignoring clusters completely. On the right-hand side, it's just a straightforward Bayesian a random effects model, pretending that those clusters that you saw on the previous slide were a fact. Like I knew them for sure. And I just highlighted two variables that were notably different, right? So ignoring the clustering means that you find that state sponsorship is not only not reliable as a coefficient estimate, but it's substantially less important. Okay. Also, kind of a reverse story here. The non-clustering model would say that holding territory is a very important variable. That is, you get about 4 more fatalities by holding territory versus not the right-hand side. It's not statistically reliable. The credible interval covers 0, and it's also smaller. So just a few notes before wrapping up. The cluster space problem is the big challenge here. So what I'm working on in several examples is having a qualitative person who studies terrorism or somebody like that say, hey, look, during those years, it's very unlikely you would have more than 10 clusters, more than 8 clusters. And I do have some papers and some folks I've talked to about that. That helps a lot. The model works fine when testing with a known number of clusters with contrived or synthetic data. What I lack is a cluster space convergence diagnostic. So the diagnostics on the MC convergence were perfectly fine for every dimension that I could look at. There, as far as I know, and if somebody out there knows of one, please let me know. A diagnostic over just the cluster space dimension. I have some ideas, but it turns out it's pretty hard. The regular Dirichlet process that I described is an R package that you can get. And I'm thinking about different ways of doing post-processing in addition to what you saw. And I think I'll wrap up there, and that seems to be right on time for Justin's schedule.
Indeed it is. All right, so thank you, Jeff, for that presentation. At this point, Jeff Gill is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. I'll start by asking the first question. So when you say the word cluster to a lot of political scientists, I think they immediately are going to think of clustered standard errors, right? They're going to, or possibly random effects models where we're thinking about groups that have non-constant variance, and we need to adjust our standard error estimates to avoid overstating the certainty of our conclusions. You seem to be using clustering in the sense of identifying unknown latent groupings. Is there any sense in which those two definitions of cluster are, I know they're not the same, but are they compatible or are they related to each other in some way? And if so, how does your approach interface with the more standard approach that most people are used to?
Yeah, thank you, Justin. First of all, I want to say I hope everybody who does that has read the King and Roberts paper. And I know, Justin, you know that paper. Cluster standard errors do not come without a price. That's not what I'm doing. Sigma squared L, if you care about that cluster variance, I'm actually estimating it directly in the context of the sampler. Okay, I'm not doing a post hoc fix in the econometric sense. So in the sampler, if that's important to you, you record sigma squared L, which I do, as it goes, and you have now a specific set of posterior distributions for the clustered standard errors. Is that what you were asking pretty much?
Well, it's also, for example, in your applied example with terrorism, you estimated the groups, and then you ran a model using those grouping variables that you came up with.
Yeah,
But if we really thought that the variance in the dependent variable in those clusters was different, we would also want to in some way account for that difference.
that's right. And I did do that. It wasn't in the model table there. So there are four clusters. I have sigma squared 1 through sigma squared 4, and I have posteriors for them. Okay. They in this particular example, they were a little different. They weren't wildly different. I have another example where they're wildly different, and that's interesting substantively, but that's data using rodents, so nobody here cares.
No. We only study metaphorical rats, not literal rats.
That's right.
Um, well, so I'm going to ask you something which I think is a very easy and obvious question for me to ask, and probably a very annoying and difficult question to answer. So any methodologist who sees this is going to say, "Oh, why don't you simultaneously estimate the clusters and the cluster definitions using the DV, and also the coefficient estimates in the DV, so that uncertainty in one propagates over into uncertainty in the other, and so that you can maybe even find different coefficient estimates." Vary according to how we define the clustering. In other words, you might find sort of joint uncertainty in the causal process and the groupings.
Yeah. So if I understand that right, I am doing one aspect of that, which is the beta sub L's, right, are going to be different.
Right.
One interesting thing to do is once you're converged, the beta sub L's, you can build a posterior distribution of them across cluster space. In other words, you can explore around clustering and then save the beta L's, ignoring the clustering at that moment. And what that essentially does is that marginalizes out curly C, right? And you get a beta distribution across cluster space.
Oh, that's interesting. Yeah. Okay, I see what you're saying.
Yeah. So I've been interested in doing that. What I found is that that process can lead to big posterior variance if the sampler visits very, very different clusters. If the sampler converges to a high posterior cluster subspace and likes to crawl around there a lot, then those posteriors for beta L marginalizing across curly C tend to be notably smaller. So
Yeah, I mean, what I was
go ahead.
originally thinking of was not so much the marginal distribution, but rather the conditional distribution. And the reason for that was like, well, so you present a version of the conditional distribution, right? Like, here's if with these clusters, here's the relationships we see. But we might also believe that, well, if I define the clusters a little bit differently, that shifts the relationships we see. And it would be, I mean, no idea how to visualize this. This is a very large dimensional space, but there might be an interesting way of putting together like, well, basically here are your choices for clustering, and then here are the different relationships that go along with those cluster definitions, and here's our posterior probability belief that each one of these sort of regimes is in place.
Yeah, that would not be hard at all. It simply depends on what you're interested in recording in the sampler. One thing I'm not doing, but I've thought about doing, is if I'm going to do that process where I'm keeping the beta L's and marginalizing out the C, I can also look at a variance covariance structure, and this is, I think, related to your question, across the beta sub L's. Like, how much do these relationships change marginalizing out cluster space?
Mm-hmm.
So the nice part about doing it with this approach is I can explore other quantities of interest at a later date.
So if you're a graduate student watching this talk and you're studying terrorism, and you're not a statistician in the sense of being a theoretical statistician, you do not read the annals of statistics. What should you take out of this talk in terms of thinking about the substantive problems of terrorism, or if you're in some other field, the substantive problems of clustering, and what should you be doing about that?
Yeah. Well, as I mentioned, terrorism data is just awful compared to other subtopics in political
Yeah,
science.
terrorists don't answer surveys.
No, they don't. And yeah, I mean, you don't want to go do too much field work either, right? Actually, John Freeman and I once tried to do this with former IRA members, but there was this project that Boston College, I guess, had where they were recording them, and they were going to release the recordings on their deaths,
Hmm.
but it ended up being a big to do between the U.S. and the British government, and
Hmm.
then everybody shut up, and
Yeah.
we couldn't do that. But I mean, terrorism data is so bad that it begs for new methodologies in the empirical sense, right? Not the qualitative substantive study.
Right.
And so if we know there are networks, let's go think about sophisticated network models. If we know there are clusters, let's go think about clustering in not necessarily in the way that I did. If we know that they change over time, right? Obviously, a time series model is appropriate. But I think just throwing the standard set of GLMs and whatnot at these sort of data is relatively unproductive, and you're going to miss important stuff.
Hmm. I don't see any questions from the audience, so I will wrap up this week's IMC. I'd like to thank Jeff for being our presenter this week. I want to remind everyone that his presentation will be posted to our website shortly after this broadcast if you'd like to share the presentation or watch it again later. I also want to invite everyone to join us next week, Friday, March 26th, when we will host a talk by Ludovic Riel of the University of Toronto. The talk is entitled Modeling Audio Data with Speaker Heterogeneity. Please see our website, www.methods-colloquium.com, to get more information about this talk. Jeff, thanks for being here today.
Well, it's safer this way, right?
Exactly. And I hope to see everyone virtually again next week.
Thank you.